Hey guys, my name is Shreyas and welcome to Simple Chemistry. In this video, we are going to be exploring heat and stoichiometry problems. Now this is pretty simple, but it needs to be discussed. Sometimes chemistry teachers might place this in thermodynamics, but I'm going to go ahead and place this right here because after everything we've learned from stoichiometry, this is not going to be much more difficult. Okay, so there's two types of reaction when we're talking about heat, and an endothermic reaction and a exothermic reaction. So an endothermic reaction is a reaction that consumes energy, so it uses energy. Okay, an exothermic reaction releases energy. There's a net release of energy. Okay, heat is typically measured in units called joules. So the heat for the unit for energy or heat is joules, J, and this is actually kilograms times meters squared over seconds squared. But we simplify that down to just joules, okay? And whenever we're looking for heat in stoichiometry problems, we treat heat just like any other reactant. And you're going to see what I mean by that when we do this example problems. So here I have an exothermic reaction example. How many joules of heat would be released by the reaction of 10 grams of C4H10 in the following chemical reaction? So before we even start, I want you to take a notice of here. We said this is an exothermic reaction. An exothermic reaction releases energy. So because of that, if you see here, the heat is on the right side, on the product side of the equation. Because it's releasing energy, it's going to be a product. That's why it's on the right side of the yield sign. That's why it is put with the products. Okay. It in comparison, a endothermic reaction will have the heat on the reactant side because it's going to be consuming energy. Okay, and we're going to look at an example of an endothermic reaction in a minute. Let's first do this. So how do we approach this problem? So we're looking for joules, and we're given 10 grams of C4H10. Let's make sure this reaction is balanced first before we do anything. So when we're looking for if it's balanced or not, we obviously don't look at to see if there's heat on both sides, because there's a net release of heat. So the law of conservation of mass says that the atoms are conserved, not the energy. Okay, within the energy of the reaction. Okay, that's completely complicated. That's a whole different subject. Let's just say that whenever we're balancing the chemical equation to check if it's balanced and if there's heat in it, we ignore heat. Okay, so just look at the atoms. So C4, so 8 carbon atoms here, and then 8 here, 20 hydrogen atoms here, 20 hydrogen atoms here, and then 13 times 2, 26, 8 times 2 is 16, plus 10 is 26. Yeah. So the atoms are balanced, so the equation is balanced, so we don't have to worry about balancing it. It's balanced for us. That's pretty nice. So let's continue with our dimensional analysis here. So first, let's convert this to moles. So 1 mole of C4H10 has a mass of, if you look at the periodic table here, let me pull out a calculator. So carbon has a average atomic mass of 12.011, so we're going to need 4 of those, plus hydrogen, has an average atomic mass of 1.008. We need 10 of those. So the molar mass of C4H10 is 58.124. Alright, from here, the reaction here is telling us that based on the reaction here, what it tells us is that for every 2 moles of C4H10 that reacts, 2,878 joules of energy is going to be released. Okay, so we can use that as a conversion factor. So that's basically the extra thing you're learning here. it's 2 moles of C4H10, which is released, 2,878 joules. So for every 2 moles of C4H10 that is reacted, 2,878 joules are released, okay? It's not based on the atom. It's not for every 2 compounds, 2 molecules of C4H10 that's released 2,878 joules. It's not. Let me rephrase that. This is not 2 molecules. Like the equation is not saying for every 2 molecules of C4H10 which reacts, 2,878 joules of heat is released. It's saying for every 2 moles of C4H10 which is reacts, 2,878 joules is released. Okay, it's based on the mole. Okay, so from here, grams of C4H10 cancels out with grams of C4H10. Moles of C4H10 cancel out with moles of C4H10, and we can just go ahead and do the math here. So let's see, 10 times 1 times 2,878 divided by 58.124 times 2. So we're getting this. And then for significant digits, this number has 3 significant digits, this number has 5, and this number has 4. We ignored these 2 numbers, 1 and 2, because they are exact numbers. Okay, so out of those, this number has the smallest number of significant digits, which is 3, so our answer needs to be rounded down to 3 significant digits. So we will notate our answer as 248 joules. Okay, now let's go ahead and look at an endothermic reaction. So like I mentioned before, if you look at the reaction here, joules is on the reactant side. Since it's an endothermic reaction, it is consuming energy, and since it is consuming energy, the heat here is going to be on the, if you look here, on the left side of the yield sign, meaning it is with the reactants because it's being consumed. Okay, that makes logical sense. So let's look at the question now. 5,230 joules are consumed in the following reaction. Okay, 2 MnO2 plus 264,000 joules yields 2 MnO plus O2. Calculate the amount of MnO2 that was consumed. Okay, so let's first make sure the reaction is balanced. So 2 manganese atoms, 4 oxygen atoms, great, because we have 2 manganese atoms here, and 1 times 2 is 2, plus 2, 4 oxygen atoms here. So the reaction is balanced. Now let's set up our dimensional analysis. So we're looking for the amount of MnO2 which is consumed. Amount, that's kind of vague. Let's go ahead and just say moles, because it doesn't actually specify if you want it in mass or if you just want it in moles. Let's go ahead and assume it's moles. Okay, and then what we're given is that 5,230 joules was consumed. Okay, so from here we know that by looking at this chemical equation, for every 2 moles of MnO2 which reacts, 264,000 joules is consumed. So we can use that as a conversion factor. For every 2 moles of MnO2 which reacts, 264,000 joules are consumed. Okay, pretty simple. And then from here, joules cancels out with joules, and we're left with moles of MnO2, which is what we wanted. And then we can just simply do the math here. So 5230 times 2 divided by 264000. We're getting this. The answer needs to be rounded down to 3 significant digits because this number has 3 significant digits and so does this one. So our answer will be 0.0396. This will be 0.0396 moles of MnO2, or manganese 4 oxide. Okay, so that's basically everything you have to know with heat in stoichiometry problems. Just make sure that you are treating the heat within the reaction as a unit, as a reactant, and you're assuming that for every mole, it's based on the mole, right? Like for this question, I explained how this reaction saying for every 2 moles of C4H10, which is reacting 2,878 joules, is released. It's not based on the molecule, it's based on the mole. Okay, if you remember that, then you're going to be fine, and you're going to get all the questions involving heat correct. Heat in stoichiometry problems is as simple as that.